Hello and welcome back to Calculus 1, starting chapter 5, and the first lecture is on areas under the curve. So what I have is a function, I have a function of some kind. This looks like square root of x, but it doesn't matter which function. And I would like to compute area from A to some B. Now, I could approximate that because I know how much this is, which is just B minus A. I can calculate this as f of B. And then I can use maybe the triangle, right? It's not good, but it would give me the rough idea of what the area is, right? So I can do that. But the trick is that we can do better, right? We can do better than that. What I can do is I can divide the area with these vertical partitions, and then turn these partitions into rectangles. So we are going to have left rectangles, right rectangles, and middle or midpoint rectangles. We're going to have three different kinds. So for the left ones, if you look at the first partition, I'm going to go to the left point that is touching the curve and draw a rectangle which is no rectangle. So that's number one. For number 2, I go to the left and I draw the rectangle. So this is rectangle number 2, rectangle number 3, and rectangle number 4. So the first rectangle in this case has area of 0 because there's no height to it. It's just a line. But the others are there. And I'm going to use the red X's over here to show error. So these x values are error. So the area that we are going to compute will be less than the actual area by the error, which are these regions that I'm not actually computing at all. So now, when I look at this, I can label my values as x0, x1, x2, x3, and x4. And the area will be approximated with area, now since we did the left rectangles, I'll put AL. And these ones are, well, first off, how much is the distance between all of these? We call that distance, obviously, delta x, because it's a difference between two values. Delta x will be x1 minus x0, which is also x2 minus x1, which is also all of the other ones. Delta x is just basically a difference between the left and right point so that we can get the width of the rectangle. So what do I have? The height is given by the function computed at x0 times delta x plus function computed at x1, that's the height, times delta x, the width, plus f of x2 times delta x, and finally f of x3 times delta x. Each one of these is the height times width. For each one. Now we see that this delta x is common, so I can kick delta x outside and just focus on f of x0 plus f of x1 plus f of x2 plus f of x3. I had 4 rectangles. I have 4 function calculations to deal with. So let's take a look at an example for this. Say area under ln x from 2 to 5. Okay. One, 2, 3, 4, 5. And we are going to use n equals 3 rectangles, so it's not just easy to compute, but quick to compute. So I'm going to draw my left rectangles. The first one is at 2, second one is at 3, and the last one is at 4. I'll put little x's. That's the error, as usual. So the area we are finding in this case is going to be less than the actual area. What do I have? Well, I hope you immediately see that delta x is equal to 1. Do we all see that? Because delta x is the width of each one of these. So from 2 to 3, from 3 to 4, 4 to 5. It's always 1. There's a formula to obtain that later, so we'll talk about it as well. So now area is approximated by area to the of the left rectangles, and that would be ln 2 times 1 plus ln 3 times 1 plus ln 4 times 1, which is just ln 2 plus ln 3 plus ln 4. We use our calculator and we approximate the value. So that's gonna be ln 2 plus ln 3 plus ln 4. Oh. ln 2 close parenthesis plus ln 3 close parenthesis plus ln 4 close parenthesis. 3.18. 3.18. Now that's approximation. That's not exact. But it's, you know, the best we can do. Now, can we do better? Sure. Put more rectangles in. If you put more rectangles in, you'll have more calculations to do, but you'll have a better result at the end. So I could do the same problem with now, let's say, cut each one of these in half. So with 6 rectangles. And the answer would not be 3.18. It would be something else, but it would be better, right? It would be closer to the actual answer. So now, what's happening with the other rectangles? Let's say I want to calculate from A to B using the right rectangles? Well, we are going to make these partition, the divisions, right? And then we are using the right corner for each rectangle to draw the rectangle, which means this. Now this is the error, as usual. And I have my 4 rectangles. Each one of them again has delta x as the width. And I have my x0, x1, x2 divisions, right? Those are some values in x. So now the first rectangle, well, area is approximated area with the right rectangles. The first rectangle now computes the function at x1 times delta x. See, it's at x1 because it's the right rectangle. So you're using the right side of the rectangle to compute the height. Right? The left rectangle computed at x0. The right one computes at x1. Plus fx2 delta x plus fx3 delta x plus fx4 delta x. So as you can see, these rectangles are all shifted by 1 because we are no longer computing at left points, we compute at right points. And again, we can factor out delta x to have f of x1 plus f of x2 plus f of x3 plus f of x4 as like a formula. Now, clearly, that formula is actually infinite, right? Because you can have as many of these rectangles as you want, and you will have to have that many calculations. Previous example, I had 3 rectangles, and this calculation had 3 terms, not 4. So we use either left or right rectangles, and then we use with as many rectangles as we need to come up with the precision that we want. Now observe that for this particular problem, your area that you are getting is bigger than the actual area, right? So we're going to overshoot now. And the previous example before this one, was undershooting, right? So the area was somewhere in the middle. Now n, lowercase n, will be number of rectangles. And the formula for delta x is simply b minus a over n. So you can always compute delta x because you need to know the interval, right, a to b, because that has to be given. And then n is, if it's not given to you, you decide. I want to do 10 calculations. Then n is 10. So you pick the number of rectangles because that immediately, right, works with the precision of the problem. So I want to read one problem from the textbook, and then we'll do the midpoint one, which is a little bit. So these two are the same pretty much. You just have to be careful whether it's left or the right. Now let's take a look at a problem. So here's what they have. Problem number 19. You are supposed to work on function v equals 1 over 2t plus 1 for t between 0 and 8, so that's your interval, 0 and 8, height A and B, and they want you to use 4 rectangles. See, the trick is that you don't have to graph this exactly. You can just put whatever graph you want and just work on partitioning, right, and drawing these things. You can use, let's use both, left and right, to see the differences and so on. So let's use both. So look for AR and AL. I'll give you a few moments and then we'll do it together. Okay, let's take a look. So we don't have to graph this exactly. I mean, this is like 1 over x, technically, graph. But it really doesn't matter. We can just draw a generic thing. It's from 1 to 8. You can even do this. You know, it's fine. It doesn't really matter because we have 1, 2, 3, 4, 5, 6, 7, 8. Right, that's 8, so from 0 to 8, and we're looking for the area. They want 4 rectangles. So delta x, the width of a single rectangle, is going to be 8 minus 0 over 4 for a total of 2. So we'll draw the rectangles at 2, like this. And this is our f of x, which is, they call it v for some kind of velocity graph, I think, in time. So what do I have? Oh, this is not delta x now, it's delta t, because it's whatever, same thing.
Okay, where do we start?
Well, we just say the left ones. AL, it's going to be delta t times v at t0 plus v at t1 plus v at t2 plus v at t3. I have 4 rectangles, 4 calculations. This is your t0, t1, t2, t3, and t4. And if you take a look at the left rectangles, that means the left rectangle is right there. Now those are the red ones. So you are using left point to draw the rectangle, therefore you are using left side to compute the height of the function, so t0 for the first rectangle. So what do I have? I have 2 times, because delta t is 2, and then I have to plug in t0 and so on, so I have 1 over 0 plus 1, plus 1 over 2 plus 1, plus 1 over 4 plus 1, plus 1 over 6 plus 1. That's 2, 1 plus 1/3 plus 1/5 plus 1 over 7. And you can quickly just plow through this using calculator if you want to. For the total of 3.35. So our left rectangles are suggesting that the area under the curve should be 3.35. Now for the right rectangles, which is AR, we are going to use the right sides to compute. So that's going to be delta t, and now we're starting at t1. Because for the first rectangle, right, t1 is on the right side, and that would give a rectangle backwards. So it goes this way now, the blue one. So we have v of t1 plus v of t2 plus v of t3 plus v of t4. And when we plug everything in, that's 2 for delta t. And then we have the same stuff, 1 over 2 plus 1. Well, actually, 2 plus 1 plus 1 over 4 plus 1 plus 1 over 6 plus 1, and finally 1 plus 8 plus 1. That will give us 2 times 1/3 plus 1/5 plus 1/7 plus 1/9. Let's see. I get 1.57. So now true area is going to be in between these two numbers. So true area is somewhere 157 to 335. I can actually tell you exactly what that area is, but you know, right now the method is, if you want to know better answer, double the amount of your rectangles or increase it by any way, doubling or tripling or whatever. What was our function? Yeah, I typed something wrong somewhere. because one of these should be, so maybe I plugged something wrong in the calculator when I computed the last thing. Plus 1/5 plus 1/7 plus 1/9. Because the computer says about 1.4, that means that this number of 1.7 should be lower. Two, 5, 7. The area is supposed to be in between the two numbers. So I can't find the mistake. I set up properly, I plugged in properly. One over 2x plus 1, right? I mean 2t plus 1 over 2t plus 1, yeah. Strange. I'll have to look into this first and then come back and talk more about it. We have one more thing, which is midpoint rectangles. So if you know, for the entire section 5.1, if you want better answer, more rectangles. Toss in more rectangles. Toss in 10 rectangles, 16 rectangles, 20 rectangles. Obviously, it increases the calculations, which is why this is something that computer science people would like to put together and go with that. Now, midpoint rectangles are really good because this is what they do. If you have a partition, let's say this is some xn and xn plus 1, so, you know, could be x3, x4, could be x10, x11, doesn't matter, it's somewhere. Midpoint rectangles would find the midpoint between xn minus 1, xn plus 1, sorry, and then on the top, draw the rectangle that goes this way. Observe that on one side it overshoots, on the other side undershoots. They are not exactly canceling each other, but the big portion of it does. So this produces a lot less error than any of the previous ones. So previous ones are technically not used ever. It's the midpoint that it's really good. So this is the one that would actually be used to approximate things, because as I said, if you take a look at the left, right, the rectangle pokes out, and everything that it pokes out is error. But on the other side, it's below function. So positive error and negative error cancel each other out, not completely, but a lot of it cancels. So it's still not exact, but it's much closer and much better than either one of the previous two, which is why you will not find previous two used when you have this method, which is better. But now there is this part of figuring out what the value of this point is, and that's a simple average of xn plus 1 divided by 2. And delta x is still the same, b minus a over the number of rectangles that you have. So, what am I going to do? Well, now, we call this m. mn, n standing for number of rectangles. It's going to be delta x times, and now you will have all of the averages in here. F x0 plus x1 over 2, right? So that's the input. Plus f x1 plus x2 over 2. Plus f x2 plus x3 over 2. And I'll put 3 dots because it goes forever. I mean, for how many rectangles you have. So that would be the formula. And you see that the step 1 is to calculate all of the midpoints. Step 1, calculate all midpoints. So let's do that. Let's say you have a square root function and you want to calculate from three to 6. So f of x is equal to square root of x on the interval 3 to 6 using n equals 3 using midpoint. Alright, so what do we do? First we partition. And then we go midpoint on all of these and we draw rectangles. So now you see that the height of each of these rectangles is computed not on the left or the right, it's computed on a middle point, which is 3.5, 4.5, and 5.5. My delta x is 6 minus 3 over 3, which is 3 over 3, which is 1. So I know delta x is 1. So midpoint with the 3 rectangles, so M3, is going to be delta x times f computed at 3.5 plus f computed at 4.5 plus f computed at 5.5. And you just need to plug in. Delta x is 1, open parenthesis, square root of 3.5 plus square root of 4.5 plus square root of 5.5. There we go. So square root of 3.5 is, let's see, $6.34. About 6.34. So that's what the area is. Now let's see if this is gonna go better than the previous one. I hope it does. We said 3 to 6, right? 6.3339. So exact is approximated by exact area, approximated at 6.3339. And my answer to the 4 decimals was 3373. So it's very close, right? It's very close. And it was only 3 rectangles. If you are to cut this in half and then do 6 rectangles, it will be even better, right? So we have this as our answer. And now we would like at the end of this lecture to learn how can we write this condensed so that these formulas are not taking too much space. It's easier to communicate, and then when you need to compute, you expand. But when you are supposed to, present it or just write the formula down, you want to have condensed way. You are used to condensed ways of writing because you memorize multiplication table. I mean, 3 times 5 is what? 3 plus 3 is 6 plus 3 is 9 plus 3 is 12 plus 3 is 15, right? Or you condense it into 3 times 5 is 15 and you're done right away. So there are benefits of condensing things in mathematics, and that is what the summation notation is for. So summation notation, and that is the symbol that you have probably seen. Looks like that. It's a Greek letter, capital sigma for S. Generally has numbers above and below. We'll see what it works. Now this is all pre-calculus stuff. By the way, in this lecture there is 0 calculus. You've seen we didn't do any integration, we didn't do any derivatives, no limits. All we did so far is A times B for rectangles, and now summation notation is again a pre-cal concept which goes into calculus, and you'll have 2 chapters on this stuff in Calc 2. So is there an easy way to write 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, right? And the answer is yes. I can just write summation of I, where I starts at 1 and ends at 8. So when you're done writing, I have to write this one more time. Because I need you to look at the board as I am saying things. Here we go. Add all i's, so summation of I. Add all i's where I starts from 1 and ends at 8. Now, can I, let's say, add all the positive numbers, 2, 4, 6, 8, plus 10. Can I do that? Well, sure I can. The way to write even numbers is 2i. And then I starts at 1 and ends at 5. Because 1 times 2 is 2 for the first number. And then I changes to 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. And the last one is 5 times 2 is 10. So, summation notation of I, where I starts at 1 and goes to some number n, is going to be 1 plus 2 plus 3 plus 4 plus dot 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 plus n at the end, because that's what it ends. But you can also have summation notation of f of I, where I starts at some value. It doesn't have to be 1, could start at 0, could start at -3, doesn't matter, can start anywhere. This would be f of 1 plus f of 2 plus f of 3 plus ... plus f of n. So we can plug in this. So I could be a counter that works directly, right? Or it could be a part of a function, could be embedded in the function. And we'll need all of these concepts. So what is the summation? Like, write it out. Where I starts at 6 and ends at 10 for 2i minus 6. So what would you write? What would be the first thing you write? Yeah, so we are plugging here values. So what's the first one? 6. So 2 times 6 minus 6 is the first one, plus 2 times 7 minus 6 is the second one, plus 2 times 8 minus 6, plus 2 times 9 minus 6, plus 2 times 10 minus 6 equal to 12 minus 6 is 6, plus 14 minus 6 is 8, plus 16 minus 6 is 10, plus, and then you can add for 20, 40, 50 as the answer. So the counter I is what you plug in for I, and every time it updates to the next integer, you have to create the new term for it. So these are your values for I. Right, those are the I values, and I values are governed by what's written on the bottom and the top of the sum, because it tells you the first value of I is 6 in this case, and the last value that I takes is 10. Now we can also put n, use 3 dots, and we also put infinity, and that's Calc2. So there'll be a lot of, all of them in Calc2 will be to infinity. Let's work on another one, and then we'll take a short break. Summation of I squared minus 4, where I starts at 3 and ends at 7. Let's see what you come up with. So what do I write first? 3 squared minus 4, very good. Plus? Yes. Yes. So we are plugging in these I values from the bottom. So we have 9 minus, that's a 5, plus 16 minus 4 is 12, plus 25 minus 4, 21, plus 36 minus 4, 32, plus 49, 45. There we go. And we add these values, so the end one set to 50, and another 50 is 100 and 115. I hope. So that's the summation notation that we are going to use in the next lecture to work out the limit definition, like equivalent, the limit definition of the integral. So we're going to use that. Bye.